Good afternoon, everyone. This is AS level standing wave assignment. In this session, we will discuss questions related to standing waves. In question 1, two waves of wavelength lambda from a single source diverge and then meet again. Which of the following situations would cause a constructive interference? The constructive interference when the path difference. So constructive interference will occur when the path difference is lambda, 2 lambda, 3 lambda, or so on. So when the part difference is lambda, 2 lambda, 3 lambda, and so on, or we can also say n lambda, it will have a constructive interference. And what about the phase difference? The phase difference for a constructive interference condition, that it should be 0 or 2 pi for constructive interference. So when we check the options, a part difference of lambda by 2, if a part difference is lambda by 2, it will be a destructive interference. When the part difference is lambda, it will be a constructive interference. So B is the right answer. Phase difference is pi by 2. Pi by 2 means it's 90 degree. So it will not be a complete constructive or destructive interference. When it is pi or 180, it will be completely destructive interference. So B is the right answer for question 1. Moving on to the next question. The structure question: an experiment is carried out to investigate the speed of transverse waves on a stretched string of length L. A vibration generator causes the string to oscillate so that a standing wave is produced. How standing wave is produced? Because when this vibrating generator produces a vibration, these vibration travel and they strike the pulley and bounce back. So two waves traveling in opposite direction give rise to a standing wave. And region where they have high amplitude, it means it's a constructive interference and it will form antinode. Where region where the two waves completely cancel out the effect of each other, there will be a destructive interference and we will have a node. So this is the antinode and here this will be a node. Now the question is, determine the wavelength of a wave on a string when vibrations as shown when length L is equals to, we have to determine the wavelength when length is given 1.7 meters. So this total length is equals to 1.7 meters. We can work out the total number of the waves. So how we can work out the total number of waves? Like this is one complete wavelength and this is the second complete wavelength. As this is a wave or distance between the two successive nodes, that is equals to lambda by 2. So three consecutive nodes, that will be lambda. So this distance is lambda. This one is also lambda. So it shows that two wavelengths or 2 lambda is equals to L, or lambda is equals to L divided by 2. L is equals to 1.70 divided by 2. So that is equals to 0.85 meters. Is it clear? The first part of question 2. The first part of question 2, in which using the length we have to determine the wavelength. In part B, calculate the speed of the wave on a string, the mass of 0.2 kilogram and mass per unit length on a string, that is given 4.5 into 10 power minus 3. So the formula which relate speed, tension and mass per unit length for a wave in a string, that V is equals to under root T divided by mu. That is the formula which we use to find the speed of a wave in a string. What is T? T is the tension. And what is mu? Mu is mass per unit length. So this is mu is given. But here mass is given. How we can work out the tension? So when you check the figure, actually the load which we used here, this mass will have its weight. So this mass is 0.2 kilogram. So the mass here is 0.2 kg, and that 0.2 kg will convert into weight. W is equals to mg, and that weight will be equal to the tension in the string. So it will be 0.2 multiplied by 9.81. This will give us the tension in the string, which will come out as 1.96. So tension in the string is 1.96 Newton. And the value for the mass per unit length is already given in the question. So the formula which we are using, V is equals to under root T divided by mu, where T is the tension, so equals to the weight. 0.20 multiplied by 9.81, that's equal to 1.60 Newton, and mu already given in the question, that is 4.5 into 10 to the power minus 3 kilogram per meter. So we substitute the value, so V is equals to under root T, which is 1.60 divided by mass per unit length, that is equals to 4.5 into 10 to the power minus 3. So this will give us the speed of the wave in this string, that will come out as 20.9 meter per second, or you can write 21 meter per second. The next part, the frequency of vibration generator is reduced until the wave pattern shown below is produced. Explain the effect that this would have on the speed of the wave in a string. So how it will have effect on the speed of the wave in a string? We are decreasing a frequency, so we have the formula. The first one, you were looking at more vibrations, so this was having high frequency and shorter wavelength. Frequency is more, wavelength is less, and the speed in that case, it was coming out as 20.9 meter per second. But now what happened? We reduce the frequency, so the wavelength has increased. So when we reduce the frequency, the wavelength increased, but what happened to speed? Because V is equals to F lambda, one is decreasing, other is increasing, so the product will remain same. So the product will not change. So the speed of the wave in a string does not depend on how many loops are there, how many vibrations are there, as it is a product of frequency, and so it only depends on the mass per unit length, like how much mass is there per unit length for the string, as well as the tension in the string. So greater the tension, greater the speed. If higher mass per unit length, smaller speed. So speed of wave in a string depends on tension and mass per unit length. Tension and mass per unit length does not change. So speed will remain same. Moving on to the next question. Two waves from a same source arrive at a point with a path difference of 3 lambda by 8. Which of the following is a phase difference at this point? So when we compare, look, when the comparison between the part difference and the phase difference, we need answers in degrees. So when the part difference is lambda, the phase difference will be 360 degrees or 2 pi radian. Now the part difference is 3 lambda by 8. So the phase difference is x. We cross multiply. So x will be equal to 360 multiplied by 3 lambda by 8 and divided by lambda. So lambda will cancel with lambda. When we find 3 by 8 of 360, that will come out as 135 degrees. So C will be the angle phase difference between the two waves. Is it clear? The next question, structure question. Active noise reduction ANR is a system used to reduce the unwanted noise. In ANR, a second sound wave is produced that cancel the first one. And ANR is used in aircraft to reduce the noise heard from the engine. On a particular flight, the noise from the engine has a frequency of 0.85 kilohertz. The graph shows a possible second wave. So this graph is showing a second wave. Determine whether this would be suitable to cancel the noise. So how we can work out, because we should use to cancel out, we should use the same frequency. The frequency of the engine is 0.85. So using a graph and the speed, we have to find the frequency. So using the graph, how we can work out the wavelength? So distance between the two successive crests, that is refers to wavelength. So when we scale this is 0.1, 0.2, 0.3, 0.4, 0.5. So the wavelength starts from 0.1 and ending at 0.5. So wavelength is 0.4 meter. And we have the formula V is equals to F lambda. So F is equals to V divided by lambda. So 340 divided by 0.4. So when this 340 divided by 0.4, it will come out as 850 hertz, or when we convert this into kilohertz, it will come out as 0.85 kilohertz. So we are using the same frequency to cancel out the noise from the engine, so it is suitable. Comparable frequency to cancel out the other wave. Otherwise, if different frequencies are there, it won't be able to cancel out completely. The next part, for a particular passenger in an aircraft, the noise from the engine travel as a wave towards the passenger from the front. So the noise is from the engine is coming in from this direction, and ANR system create a second wave that is directed towards the passenger from the side as shown. Explain how this leads to sound being cancelled from one ear but louder for the other ear. So what is the reason why one of the ear it will be it cancelled and the other ear it will be loud? So it is related to interference as well as like formation or cancelling of the wave, interference as well as diffraction. So as you can see in the figure, the sound from ANR has to diffract will diffract to reach right ear, that ear on the right hand side. This sound will diffract to reach the right ear, this side, and destructive interference when destructive interference will take place, and loud sound is there when constructive interference. And in destructive interference, waves are antiphase, and in constructive interference, waves are in phase. So this is basically what happened. The sound which is from ANR, it has to diffract and reach the right ear, and sound which undergo a destructive interference will cancel out, so no sound, and louder sound because constructive interference, and destructive interference is there because waves are anti-phase, and constructive interference when they are in phase. So basically what happened, and another thing, when this distance between the ears is half of the wavelength, then it will lead to destructive. Why it will lead to destructive? Like example, here the wave cancel out each other when it meets. They cancel out each other, so there is no sound. But when it travel half of the wavelength, then likely which type of interference will take place? Constructive interference, because initially it was a destructive, then the after half wavelength it will be constructive, because when you draw the figure, so for a destructive interference, like if one wave is traveling in this manner, the other waves completely cancel out, the destructive interference will take place. But what happen in, if we further, if the distance of one wave, like distance between the ear is lambda by 2 or half of the wavelength, then what happen? There will be a shifting of interference, like it will be a constructive interference on the other side, as now the two waves, one of the wave is having this same phase, but the other one, blue, which is coming from the ANR system, will join with sound from the engine, so now they will undergo a constructive interference. So at this side it will be a loud sound due to constructive interference. So the distance between the ears should be half of wavelength. Is it clear? Discussion about ANR. Any doubt in this? So when the two waves are traveling, they cancel out, but because the distance between the ears is half of the wavelength, so when they meet at this point, it will have a constructive interference as the two waves are in phase, and here the two waves are anti-phase. Is it clear? Any doubt in this part? Moving on to the next question, also a structure question about the standing wave, how the standing wave is produced. When this vibrating generator produce the vibration travel and return. The two waves traveling in opposite direction give rise to a standing wave, which will produce nodes and antinodes. A student investigated how the frequency vibration of a strings vary with the tension in a string. The student connects a connected masses here to one end, that is to apply a tension, and other end the vibrators are shown. A signal generator was connected to the vibrator. A signal generator generate the signal generator was adjusted until the standing wave was produced. The standing wave had nodes at both ends. The length of a string is L and antinode in the middle. Explain how node and antinodes are created. So basically, you have to explain the idea of formation of node and antinode, or explain the idea of interference. So what happened? The two waves traveling in opposite direction interfere with each other. Then nodes are the point of zero or minimum amplitude formed by destructive interference and antinodes are points of maximum amplitude formed by constructive interference. So this is basically what happened uh, about the formation of standing wave in a string. Then the next part, a student changed the weight applied to a string and adjusted the frequency of a signal generator until the same stationary wave was set up. The student plotted a graph for f square against w, explained why the graph was a straight line and passing through origin. So we have to adjust the equation so that, and the graph between f square and w, the gradient should be constant, so we can say that it is a straight line which is passing through origin. So how we can work out this? We'll use different equations. We know, as we discussed in the last question, that speed of the wave in a string v is equals to under root t divided by mu, where t is a tension, or you can also say weight. And we know according to wave equation, v is equals to f lambda. So both v's are representing the speed. So we can compare these two equations. We can say f into lambda. If we compare equation A with equation B, then we can say f into lambda is equals to under root t divided by mu. So instead of t, I can write w because tension is equals to weight. So I can say weight divided by mass per unit length. When I square both sides, so if we square both sides, the square will cancel with root. So it will be f square lambda square is equals to weight divided by mu. Or we can say f square is equals to weight divided by lambda square and mu. And if we rearrange this equation, we can say f square is equals to 1 divided by lambda square mu into w. When we compare with equation of straight line y is equals to mx, so on y-axis if we have frequency, so on y-axis if I have frequency, on x-axis if I have weight, so when we have weight on x-axis, what will be the gradient? The gradient for us will be equal to 1 divided by lambda square and mu. Lambda is constant, mu is constant, so gradient will be constant. And here y it is a straight line passing through origin because the y-intercept is 0. There is nothing in the y-intercept, so y-intercept is equals to 0. So the finally when you conclude, you will mention y-intercept is 0 and gradient is constant. So it will be a straight line which is passing through origin. Is it clear? This part B, that how we can show that the graph between the f square and the weight or the tension will be a straight line which is passing through origin, as there is no y-intercept is 0, as well as it is a straight line because the gradient is constant. Moving on to the next part, describe a method that could be used to confirm that the frequency value stated on the signal generator is correct. So how we can work out that the value which is mentioned here for a signal generator is correct? So we can record the vibration by using a camera, and use time period to find frequency. Or you can also use cathode ray oscilloscope CRO and find the time period, and using a time period you can find the frequency. In part D, the weight is equals to 80 Newton, frequency is 659 Hertz. Calculate the mass per unit length, and the length of the string is given 0.32 meters. So we need mu, the value of the mu, where mu is equals to mass per unit length. And we just compare the two equations. We just compare that f lambda was equals to under root t divided by mu. When I square f square lambda square is equals to t divided by mu. So t is there, f is there, but how to get the lambda? Because in the beginning they mentioned it is vibrating, like forming nodes at the end, and antinode is there at the center. So when node is at the end and antinode, the distance between the two successive nodes, that is lambda by 2. So basically lambda by 2 is equals to L, or lambda is equals to 2L. So in place of lambda, we can write 2L. So first we can find this lambda, which is equals to 2L. So 2 multiplied by value of L, that is given in the question, 0.328. So 2 multiplied by 0.328, that is equals to 0.656 meter. So we have lambda, frequency is there. So 659 square, 0.656 square, 80, and mu. So we need mu. Mu is equals to 80 divided by 659 square into 0.656 square, and this mu will come out as the mass per unit length, which will be kilogram per meter, as 4.3 into 10 to the power minus 4. 4.3 into 10 to the power minus 4 kilogram per meter. Question 6. A student investigated the superposition of water waves in a ripple tank. There are two sources, S1 and S2, which are in phase. The diagram shows the position of the successive crest. Explain the type of superposition take place at A and at B. So at A, which type of superposition will be there? So when we work out, so it will be a constructive interference. Why constructive? Because they mentioned this. These are the wavefront. It is representing at A which type of interference will be there. How we can work out? These are the wavefront. So when I draw the wavefront, like example, this is representing crest. So the trough, the red line is representing the trough for source 1. So this red line is representing the trough for source 1. So, and the dark line is representing crest for both. So the trough, this is the trough for source 1. And when I use blue lines to represent the trough for source 2, so this will be the trough, because between the two crests, there will be a trough. So when I draw the trough for source 2, you can see trough is joining with the trough. So when trough join with the trough, which kind of interference we'll have? We'll have a constructive interference at A. But at B, what is happening? The trough of source 1 is joining with the crest. So they are in anti-phase. So which type of interference will be there? At B, it will be a destructive interference. Is it clear, the idea? The type of interference for position A and for position B. So for position A, it will be a constructive interference. And for position B, it will be a destructive interference. And because the two waves are in phase, at A, and two waves are antiphase at B. In question 7, a recorder is a musical instrument with a mouthpiece at one end. So there's a mouthpiece at one end and the open end is there. It's an open pipe. When a musician blow into a mouthpiece, a standing wave is produced in the air column inside. So here it's antinode, node and antinode. The standing wave has antinodes at both ends and node will be there at the center. Calculate the frequency of a sound produced by this standing wave. Speed is given and the length of the recorder is given. So using a length of the recorder, we can work out the wavelength. How we can work out the wavelength? Like this total length is given 23.6 centimeter. And what is the distance between the two successive, like distance between node and antinode is quarter of the wavelength. This is lambda by 4. And distance between node and antinode is also lambda by 4. So basically distance between two successive antinodes is lambda by 2. So we can say that the lambda by 2 is equals to L, or lambda is equals to 2L. So lambda is equals to 2L. So 2 multiplied by the length, which is given in centimeter, we have to convert into meters. So 0.236 meter will be there. So that will come out as 0.472 meter. That's a wavelength. Now we have the wavelength, the frequency is there. So we can use the formula. We know the speed, so we can find the frequency. So we have the formula V is equals to F lambda. F is equals to V divided by lambda. The speed is 330 and the wavelength is 0.472. So it will come out as 699 hertz as a frequency of a wave produced in this column. The recorder is made from 3 separate sections that slide together as shown. So 3 separate sections slide together and make this whole recorder. A musician play the recorder and produce the same frequency as in A1. The temperature of air increased. As the temperature increased, the speed of the wave also increased. Explain how musician can adjust the recorder to produce the same frequency. So musician want to produce the same frequency. As the temperature increase, the speed is also increasing. So we have the formula V is equals to F lambda. So we want frequency constant. So if I want frequency constant, we have the formula V is equals to F lambda. So if V is increasing, the wave, or we can simply say frequency is constant, V is directly proportional to lambda. So if V is increasing, lambda should be increased so that the frequency will remain constant. So to keep the same frequency, the wavelength should increase. And how we can increase the wavelength? As we know, in the first part, when we calculated the wavelength, the lambda was actually equal to 2L. So if we want to increase the wavelength, we should increase the length. So the length of the recorder must be increased. And how we can increase the length of the recorder? By loosening the section of the recorder or by sliding the recorder section further apart. Is it clear? This concept that how we can keep the frequency constant. So we can slide the sections apart so that it will be a longer and produce the same frequency. The sound is traveling through air, but formation of antinodes depending on the open column. The ends which are open, because basically what we want, this speed, the wave is traveling faster. So if wave is traveling faster, we should increase the distance between the parts. Next part, on a violin, a standing wave is created when a string is plucked. A violin string has a fixed length, but the tension can be adjusted. When a string is plucked, it produces a sound of frequency 432 Hz and adjusted to produce a sound of frequency 440 Hz. Calculate the percentage increase in the tension. So what is the percentage increase in the tension? We have to calculate that. So we have the formula. As I mentioned, this V is equals to under root T divided by mu. The length is kept constant. So when we compare with the equation, as we know, it is a wave in a string or a wire. So V is equals to F lambda is a wave equation, and V is equals to under root T divided by mu is the equation used for particularly wave in a string. So when we compare these two values, so we can say F lambda is equals to under root T divided by mu. So F lambda is equals to under root T divided by mu. When we adjust this, we are changing the tension and the frequency is changing, but the length is fixed. So if the length is fixed, this is mu is equals to mass per unit length. So from this equation, what we can conclude, we can say that if I square the equation both sides, so it will be F square lambda square is equals to T divided by mu. So I can say the relation between frequency and the tension, they are directly proportional. With square, like I can say F square is proportional to T. So and when according to this, how we work out F square proportional to T, because F is a frequency and T is a tension, greater the tension, greater, like if we double, if we want the frequency, like if we double the tension or if we double the frequency, the tension should increase by 4 times, because F square is proportional to T. So when we want to work out the percentage increase, there are two ways to do this question. You can find the frequency for each, or you can find the tension for each. The frequency is given 432 and this is 440. So what we can do, we can work out the tension for each case, and then we can take a difference in the tension divided by the original value. We can find the percentage increase. The second way to work out the percentage increase is by taking a ratio of the two. As we know, f square lambda square is equals to under root t divided by mu. And they mention in this question that when a violin string has a fixed length, so length is fixed, L is constant, and tension can be adjusted, so we can adjust the T. So first what we will do, we will find the tension for 432 hertz, and then we will find the tension for 440 hertz, and then we'll calculate the percentage increase in the tension. Like, or the second way, we can just use the values as we know the relation between that T and F square. So T is proportional to F square. So when two quantities are proportional, their ratio should be constant. So T divided by F square is equals to K. Or we can say that T1 over F1 square is equals to T2 over F2 square. Because like first tension divided by first frequency square equal to second tension divided by second tension square. So if you find the ratio of T2 divided by T1, so T2 divided by T1 is equals to F1, T2 divided by T1 is equals to, as they are constant, so F2 will, F1 will be there. Yeah, for F1, F2 by, that's right, for, because the ratio is constant. So it is, if it is T2 divided by F2 square is equals to T1 divided by F1 square. So when we cross multiply, T2 divided by T1 is equals to F2 square divided by F1 square. So F2 square, that is 440 divided by 432 square, will get as 1.037. So the new value is coming out, the ratio changed to 1.3037. So in terms of percentage increase, like how much in terms of percentage increase is there? It is 1 minus or 1.037 minus 1, that is equals to 0.037, and in terms of percentage it will be 3.7%. Is it clear, this question? So these are the questions related to topic standing wave. Next session we'll discuss more questions from this assignment.